Dear students, greetings for the day. Today we will study enzymes. Common enzymes in foods: polyphenol oxidase, plant cell wall degrading enzymes, proteases, lipases, peroxidase, catalase, amylase, ascorbic acid oxidase, lipoxygenase. Temperature dependence of enzymes. Every enzyme has an optimal temperature for maximal activity. The effectiveness of an enzyme activity for most enzymes, it is 30 to 40 degrees Celsius. Many enzymes denature greater than 45 degrees Celsius. Each enzyme is different and vary by isozymes. Often an enzyme is at its maximal activity just before it denatures at its maximum temperature. The effect of temperature is twofold, from about 20 to 35 to 40 degrees Celsius for enzymes, from about 5 to 35 degrees Celsius for other reactions. Q10 principle: for every 10 degrees Celsius increase in temperature, the reaction rate will double. Not an absolute law in science, but a general rule of thumb. At higher temperatures, some enzymes are much more stable than other enzymes. Enzymes are sensitive to pH. Most enzymes active only within a pH range of 3-4 units. Catalase has max activity between pH 3 and 10. The optimum pH depends on the nature of the enzyme and reflects the environmental conditions in which enzyme is normally active. Pepsin pH 2, trypsin pH 8, peroxidase pH 6. pH dependence is usually due to the presence of one or more charged A at the active site. Number of the enzyme commission: 3 hydrolysis, class 2 glucosidase, subclass 1 hydrolyzing O-glycosidic bond, subclass 1 specific enzyme. Oxidoreductase, oxidation, reduction reactions, transferase, transfer of one molecule to another, that is functional groups. Hydrolase, catalyze bond breaking using water, i.e. protease, lipase, lyase, catalyze the formation of double bonds, often in dehydration reactions. Isomerase, catalyze intramolecular rearrangement of molecules. Ligase, catalyze covalent attachment of two substrate molecules. A transferase is any one of a class of enzymes that enact the transfer of specific functional groups, for example a methyl or glycosyl group, from one molecule, called the donor, to another, called the acceptor. They are involved in hundreds of different biochemical pathways throughout biology, and are integral to some of life's most important processes. Hydrolase is a class of enzyme that commonly perform as biochemical catalysts that use water to break a chemical bond, which typically results in dividing a larger molecule to smaller molecules. Some common examples of hydrolase enzymes are esterases including lipases, phosphatases, glycosidases, peptidases, and nucleosidases. In biochemistry, a lyase is an enzyme that catalyzes the breaking and elimination reaction of various chemical bonds by means other than hydrolysis, a substitution reaction, and oxidation, often forming a new double bond or a new ring structure. The reverse reaction is also possible, called amycal addition. For example, an enzyme that catalyzes this reaction would be a lyase. ATP camp plus lyases differ from other enzymes in that they require only one substrate for the reaction in one direction, but two substrates for the reverse reaction. Isomerases are a general class of enzymes that convert a molecule from one isomer to another. Isomerases facilitate intramolecular rearrangements in which bonds are broken and formed. The general form of such a reaction is as follows: ABBA, there is only one substrate yielding one product. This product has the same molecular formula as the substrate but differs in bond connectivity or spatial arrangement. Isomerases catalyze reactions across many biological processes, such as in glycolysis and carbohydrate metabolism. In biochemistry, a ligase is an enzyme that can catalyze the joining of two large molecules by forming a new chemical bond, usually with accompanying hydrolysis of a small pendant chemical group on one of the larger molecules or the enzyme catalyzing the linking together of two compounds. For example, enzymes that catalyze joining of CO, CS, CN, etc. In general, a ligase catalyzes the following reaction: AB plus CAC plus PO, sometimes AB plus CD, AD plus P plus C plus T plus E plus F, where the lowercase letters can signify the small, dependent groups. Ligase can join two complementary fragments of nucleic acid and repair single-stranded breaks that arise in double-stranded DNA during replication.